everyone, welcome back to another episode of the problem solving series. Today is going to be our last video talking about our rotational analogs to the linear physical concepts, and we will be going over rotational kinetic energy as well as rotational momentum. So we'll of course talk about equations and concepts, and then we'll go into solving some problems. So first let's talk about rotational kinetic energy. So previously we have talked about linear kinetic energy, which is going to be 1/2 mv squared. For rotational, we're going to swap out all those linear quantities for the rotational analog. We still use the capital K or the capital KE to denote kinetic energy. If you want, you can put like a little subscript rotational or ROT just so that you know which one is which. I think I've seen like a capital KR and a capital AT for translational and rotational. That's pretty common. And so our KR is going to be 1/2 I omega squared. So like in the moment of inertia video I mentioned, kind of that step of calculating I being baked into other questions focused on other concepts. Both of these are going to be concepts that do that because they can both involve I. So rotational kinetic energy definitely does. Rotational momentum may or may not, which we'll get into next. But yeah, so K rotational is our 1/2 I omega squared, and anytime you have something, so if you have something just spinning but is somehow like stuck, so I'm trying to think, and the only example that's coming to mind is if you're rolling like toilet paper, as cats love to do. They love to just roll that toilet paper roll off. So if they're pulling all the toilet paper off as the roll is spinning, it would only have rotational kinetic energy since the center of mass isn't moving. But a lot of the times you'll have things like cylinders or hoops or balls going down a ramp or doing something, and in which case the center of mass is going to be moving as well as the object rotating around that center of mass. So when you set up your conservation of energy equation, you just want to make sure you're including both kinds of kinetic energy. One of the really big things that I see with these types of problems is being able to go back and forth with converting and writing angular quantities in terms of linear quantities and vice versa. So just make sure you're remembering and keeping track of how to go back and forth between the two. I'll make sure the example problem that I do will kind of show an example of this idea, but just, keeping track of all of going back and forth between linear and translational is just really key to a lot of these rotational concepts. Then for rotational momentum, because this is a vector quantity, we're going to have two different ways that we can write this out, similar to torque. So we can either write this as the momentum cross R. Typically you won't have a rotational problem where you have to worry about taking any sort of sign, so momentum is almost always the linear momentum. I can't think of an example where the linear momentum wasn't just perpendicular to R. So you shouldn't have to worry about that too much, but do keep in mind still, just in case, that is a cross product. So keeping in mind that you want to have the perpendicular component when using that. So angular momentum or rotational momentum, capital L, can be equal to P cross R. Typically that's written as just MVR. Again, taking out that angular, thinking of that P and that R of just being perpendicular to one another always. And then if instead we substitute in looking at the linear momentum equation, that's just equal to mv. If we swap out those linear quantities for their rotational analogs, we get capital L is equal to I times omega. So again, this is another case where you might have to go back and forth between linear quantities and rotational quantities, and I'll be sure to show that in the example problem that I do next.
A person is riding a unicycle at a constant speed of 10 meters per second
They then slow to a stop after the wheel goes through 4 full rotations. What is the torque needed to slow down the unicycle? And we can treat this wheel as a hoop. So we'll go ahead and draw our picture. So we're going to have our initial state with our wheel moving at v equals 10 meters per second. And then we will also have our final state where our wheel is stationary, so our v equals 0, but we've gone through, so we don't have really a variable for the number of rotations, so I'll write that we've gone through 4 full rotations, and I also will just go ahead and highlight some of our givens in the problem itself. So we have our initial constant speed, 4 full rotations, slow to a stop. We're solving for torque, and then we know that it's a hoop with that mass and that radius. So let's, before we take stock of some of these other things, just take note of what types of energies we're going to have to start and then the types of energies we're going to have at the end. So initially we're going to have kinetic energy translational, and we're going to have kinetic energy rotational because we can assume that this is rolling. We will also be having some work acting on the wheel from the initial state to the final state, and then when we get to the final state, everything is going to come to 0. And then we will go ahead and just set those two sides equal to each other. The next step, I'm just going to substitute in the expressions that we have for each of the kinetic energies and the work in terms of torque, since torque is what we're interested in here. So we'll have 1/2 mv squared plus 1/2 I omega squared plus tau delta theta equals 0. And now I'll kind of draw a little section over here so we can now write down some of our givens. So since it's a hoop, that's going to tell us that the moment of inertia we can use is mr squared. Our m is 1 kilogram, our r is 0.3 meters, our v is 10 meters per second. So really typical for these types of problems is that we do have these two different types of kinetic energies, but they're only explicitly giving you either the angular velocity or the tangential velocity. But because the moment of inertia is related to mass and radius, and also omega is related to v and radius, we can actually get things in like terms and be able to solve this problem. There's a lot of interconnected variables once we get to rotational and translational stuff. So I'm first going to go ahead and substitute in, well, in the next step, I'm going to substitute in that mr squared for I. So mv squared plus 1/2 mr squared omega squared plus tau d theta equals 0. The other thing we can use is the fact that since v is equal to omega times r, this r squared and this omega squared would be the same thing as a v squared. So if I squared that other equation I wrote all the way to the right, v squared is omega squared times r squared, so we can make that substitution as well. 1/2 mv squared, and that'll end up being another 1/2 mv squared plus tau delta theta equals 0. So now we are free to combine those two energy terms that we have. That'll just end up giving us an mv squared plus tau delta theta equals 0. So we know m, we know v. Let's talk about our delta theta now. So like I said, we don't have a variable for rotations. I guess you could call it just like capital N to count the number of rotations. But usually the way that I like to think about that is that if we have 4 rotations, I will convert it by saying that 2 pi radians divided by 1 rotation to switch units is going to give us 8 pi radians, and that's going to be our delta theta. So first, before I go ahead and plug everything in, I'm just going to rearrange in terms of variables first. So we can subtract mv squared. We get tau delta theta equals negative mv squared. Then we can divide out delta theta to get tau equals negative mv squared over delta theta, and now I'll plug everything in. So we have negative 1 10 squared over 8 pi, which gives me a torque of 3.98 newtons times meters. Okay, this is a long one, but I wanted to be able to hit a couple different types of angular momentum problems kind of all in one shot, so I might have to go and do a new page. And I guess I'm also going to be doing a little educating on throwing events, which might not be correct because I threw for 1 spring in high school and that was it. But in some throwing events, athletes will spin to gain angular momentum before releasing the object. In shot put, the object is located very close to the body, about 2 meters from the axis of rotation. What amount of torque would an athlete need to launch the shot put at a speed of 50 meters per second in 5 seconds? So let's just tackle the first part of this problem and not even worry about the second part just yet. So we're going to assume that we can ignore any of the angular momentum going into the athlete itself. We just want to see what can be transferred over to the ball. So we are simplifying this. So if we consider when we're starting, so before we just have the ball located some short distance away from the axis of rotation being held, so we have nothing moving. So our momentum angular is going to be equal to 0. I write it as L initial. And then after, right before it's released, now this has gained, so imagine it's going in. It's been spinning in a circle this way. I guess it doesn't matter what direction, but we'll just put it that way. And then right before it's released, it will have accumulated some omega. So we'll now have our L final equals some I times omega, where I is going to be the moment of inertia of the ball. So we have those two things set up. Then in terms of torque, using the analog of impulse, we can say that the change in angular momentum is equal to the torque times the change in time. So our L final minus L initial is equal to torque times delta T. I guess I'll write down our list of givens as well. Oh, I didn't give a mass for these. Ooh, shoot. Actually, there's some standardized weights for these that I don't know, so I'm just going to make up. They're relatively heavy, though. I'm going to say it's going to be 6 kilograms. I already gave the R 0.2 meters. Our V, so I did a little tricky thing. I gave you V instead of omega, but they're related. And our delta T is going to be 5 seconds. So our V initial is 0, but our V final is I times omega. The other equation that we have for when we can treat our system or our object as just a particle moving at some distance away from some center like we do have here is we can write our momentum angular as momentum cross r, which would just be MVR for the situation that we have here and any situation you would come across in your problems. They're not going to give you anything more complicated than that, but you just have to be able to identify when you can use it. So it's only when you have an object rotating around in this way. You wouldn't, if this was just some ball spinning on its axis, we couldn't use MVR. We would have to only be able to use I omega. But in this case as well, you get the same relationship back, since for the I, for a particle moving, rotating some distance away from the center, we can write that as mr squared times omega. Let me fill in the rest of that equation. I'm going to drop the 0. And the r squared times omega, or if we separate those r's so that we have mr r omega, that r times omega is our linear velocity, so we get an mrv, which is just mvr but rearranged. So either way we're good. Things check out. From this point, we just want to divide our delta t because we're interested in solving for torque. And then we can substitute in. So we'll have 6 times 0.2 times 50 over 5 is our torque, which is going to give us 7.98 7.96 newtons times meters. Okay, I realized I made a calculator error in the first part of the problem, so I've corrected that now. Our answer for torque should be 12 newtons times meters, and now we could go ahead to part 2. So let's compare how the launch speed is going to be different if now we're switching to hammer throw, but we're going to provide the same torque in the same amount of time as we just did in this first question. The only thing that's changing is our radius. So I'm just going to redraw the picture that we had. So our initial is again our axis of rotation, our mass some distance away, but our initial everything is 0 because we're at rest. Our final, after we've had some torque in some amount of time, right before release, this will now be moving with some omega and consequently some v when it's let go, and we'll have L final equal I omega, or like we said, because of the situation we have, we can write that as MVR as well. And our torque is 12. Our change in time is 5 seconds. Our radius is now 1 meter. Our mass is still 6 kilograms. And we'll solve for omega n for v. So we'll also set up here that L final minus L initial equals torque times delta t. Our L initial is 0. We'll use I omega this time to get omega first. Then to get omega by itself, we'll divide by moment of inertia. And then we'll substitute in that moment of inertia for this situation is going to be mr squared. At this point, we can plug in our numbers. So we'll have omega is 12 times 5 divided by 1 times 1 squared. oh, nope, 6 times 1 squared. Which is going to give me 10 radians per second. And then next to that, we can say that the velocity is angular velocity times radius. So our velocity is going to be 10 meters per second. So if you provided the same torque to hammer throw as you did to shot put, it would leave with a much, much slower velocity when you release it. Obviously, there's many more complex things that go into throwing. This is a toy example. Shot put and hammer throwers, don't come for me. All right, and that's all I got for rotational energy and rotational momentum, and that completes our look at these rotational analogs. So just as I mentioned before, I will kind of put obviously the equations that we talked about in this video, but kind of all of the rotational and linear quantities and how they're related to one another. I'll put that before Howitzer's outro. And until next time, happy physicsing. Bye, guys.
What are you chewing on? Hi. Oh, stick? Can you say bye to the kiddos? You saying bye? Yeah, that's my shoe.